All right, so here we are. We finished up chapter 3 last week. That went pretty well. So we're moving into chapter 4. Chapter 4, we'll start talking about probability. And we'll begin fairly easy with some basic things in 4.2. We're going to get the addition rule today in 4.3. So we're going to get 2 sections today. Your quiz will cover both sections on Thursday. Okay, so basic probability is where we're going to be here. So this is more maybe like Algebra 1, Algebra 2, early on probability stuff. Nothing really complicated in these 2 sections today. As we progress through this chapter, the probability gets a little tougher because the counting up the events is a little tougher to do. So, but it all stems off of this basics that we'll get here in the first section. Okay, so probability of an event, and we're going to talk about how to interpret that. So a lot of what you did in algebra class with probability, did much with it at all, was basically just finding the probability of that. We didn't do much in terms of interpreting what was happening with it. So we're going to be building up to interpreting that. We're going to relate this back to those distributions later on and probability of events inside of those distributions, as well as we kind of get throughout chapter 4, 5, 6, 7, and 8. What relates together. There we go. All right, an event is a collection of results or outcomes of a procedure. That procedure might be flipping a coin. You know, that's and the outcome is it landed on tables. That's an event. An event is the flipping of the coin or rolling of a dice, drawing a card from a deck. That's the collection of the event that's happening. So results or outcomes from of a procedure, that procedure being, whatever we're doing, if we're rolling a die or picking a card or flipping a coin, that sort of thing. That's a procedure. Simple event, it can't be broken down into simpler components. Flipping a coin is a simple event. Rolling a die is a simple event. Simple events are what we long for in probability world is simple events. Those are what you want because it's much easier to calculate things when things are simple. Compound events are a little tougher to do, and we'll get into those. Simple events, though, are mainly what we're going to be dealing with today. Simple events can't be broken down into simpler parts or multiple steps. I think it's a good way to think. A simple event is a single thing that happens. A sample space, when we're talking about probability, is all the possible simple events. So if it's flipping a coin, the sample space is heads and tails. That's it. Okay. If it's drawing cards, the sample space is each individual card. It's a sample space. Rolling a die would be the numbers 1 through 6 are possible. That's the things that could happen out of that. Sample space are the outcomes that can't be broken down any further. So that goes back to the definition of a simple event. Something can't be broken down any further. The sample space is the listing of all of those things that could happen. That's what when it says, if you get a question that says, write the sample space for this event, that means write every possible outcome. So if it's a coin, you write heads, you write tails. That's your sample space. All right. Here's a couple of examples of that. A little bit different examples. If we use boy and girl, B for boy and G for girl, obviously. As a procedure is a birth of a child. A simple event is that you had a girl. Or another simple event would be you had a boy. Okay? And the sample space for that is boy or girl. One single birth. If you talk about 3 births, so my parents had 3 kids, and 2 boys and 1 girl is an event in that procedure of 3 births. the possibilities for that are boy, boy, girl, a boy first, girl, then a boy last, and then a girl first, and then two boys in a row after that. Those are the simple events that could produce two boys and a girl. The sample space are all possible ways of having three births. So you could have all boys, two boys and a girl, boy, girl, boy, you know, that all of that stuff, the different ways for doing three births out of that. So listing the sample space are all the possibilities for that. Okay, for three births. There are how many births? 1, 2, 3, 4, 8 possible ways that happen. My parents didn't choose this, but they got the boy, boy, boy version. It's fun. Cameron, that food on. I did. Awesome. Interesting choice of footwear. Yep. Yeah, that's cool. All right, so you don't call it shit. All right, notation wise, capital P means find the probability. Okay, so if you see capital P, they're just saying find probability. And then A, B, and C, or whatever other letter they use, is denoting a specific event. Event A might be that you have a boy. Event B might be that you have a girl. Event C might be the next birth or something like that. So when we're dealing with that, this is how they'll denote, find the probability of a certain event. Probability of A denotes find that probability of a event happening. A, they'll tell you what that is. What A stands for, what you're trying to find the probability of. So you're dealing with a deck of cards, what's the probability of drawing a heart, out of the deck, one card at a time. That so it'd be P of a heart. That'd be the right. Real simple way to know that. Okay. Basic rules for computing probability. So that big thing at the bottom there, that's more what you want to hang on to there. Probability of A is the number of times that event occurs, and over the number of times the procedure was repeated. When we're dealing with probability, observing or conducting a procedure, we count that number of times that we draw a heart out of the deck. And based on these actual results, we get an approximated probability out of that. So relative frequency of approximation on probability. So, the same probability you've been dealing with your whole lives. Any parts are in the deck. 13, right? And 13 out of 52 is probability to draw a heart. It's the same probability that we've been dealing with. Here's the classical approach to probability. It's the same idea, the number of ways that something can occur over the number of different simple events. So that's that 13 out of 52 that you would then reduce to get your probability for drawing a heart or a diamond or a spade or a club. That's one thing in the deck of cards. I say this like we know how to play. We've got decks of cards. Something I come to realize over the years, not everybody plays cards and it knows what's in the deck. So we might need to 13 out of 54. If you use jokers, yes, it's 13 out of 54. That's true. The jokers are they're not of any particular set. They're just another number of suit, and they're just another card, an extra card there. So usually we throw those out. When we talk about it, if it says use a standard deck of cards, no jokers in there. So it's just 13 hearts, 13 diamonds, 13 spades, 13 clubs. That's a standard deck of cards. Jokers are not involved in the standard 52 card deck. So in different signal events, and each of those has an equal chance of occurring. That's highlighted in red for a reason. Okay, it's an equal chance of occurring for it to be that classical approach to that equally likely outcome. So if I shuffle the deck, when I just reach in there and pull out a card, it's equally likely that I pull a heart as it is if I pull a club or a spade, or as long as you don't have a good deck. true. We're hoping for simple random events, so the shuffling of the deck should be fair and all that sort of stuff. That's what we're hoping for this. Equally likely outcomes. Rolling a dice, a set of dice, you have two, 1 through 6 on each one. They equally likely, meaning that they're not loaded dice and that one side is weighted in order that there's been an angle filed on one of the corners so that it will roll over a certain way. Those sort of things make it not equally likely outcome. So equally likely outcome, we think. Subjective probabilities are estimated relevant circumstances. So we don't do this a whole lot. Rule 3 is not something we tend to do. We're going to spend most of our time dealing with Rule 2 about equally likely events happening. That's where we're going to spend most of our time because those are much easier calculations and much more justifiable answers to that. That makes life a lot easier when things are justifiable, especially in a math class. Event A, it's estimated by relevant circumstances. It's very vague, but all right. Law of large numbers. You may have heard this before, but as a procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability. The actual probability is Rule 2. We actually have 12 hearts or 13 hearts out of 52 cards. If you actually sat here and drew cards, the more times that we all did that, would shuffle the deck in between each draw, the more likely that we're going to end up with probability of 13 out of 52 for drawing cards. So the more we do something, the more likely it is to go to our, what we'll say is theoretical probability. The relative frequency is more like a experimental probability. It's actually what happens, where the simple event probability, like for Rule 2, is more of a theory. Theoretical probability is what should be happening. Okay? Law of large numbers says as we do more of that procedure, the more we roll a rolling die, the more likely it is that we end up with a ratio that's equal to all possibility 1 through 6. All right, here's an example. Back to that 3 children are born. There's our sample space. Assuming that boys and girls are equally likely, find the probability of getting 3 children that are the same gender. Okay, so in the sample space, how many of them are the same gender? All 3 of them. 1, 2. There are 8 possibilities in the sample space. 2 out of 8. Real simple idea. So if you got the sample space, you look at it, and that's 7th grade stuff. Simulation is a procedure, that we're simulating what could happen. Your calculator actually has some simulations that you can run. There's an app on most of them. Not everybody's got that app, so we don't use it very much, but there's an app sometimes that you can run probability simulations on. There's also several programs out there that are made for statistical analysis that have probability simulations that you can run for us and create some similar results to what we would expect if we actually carried out the experiment ourselves. All right. Probability limits. It's impossible. If it's impossible, the probability of that event is 0, right? If it's certain, then it's a 1. Because probability is in terms of decimals, 100% probability is 1.00. Right? So where our events can be anywhere between 0 and 1. Right order. So decimal number between 0 and 1. Okay. If it's impossible, then it's a probability of 0. If it's certain that that event is going to happen, it has to happen, then the probability is 1. The most. too much, but it's just one of those rules where we've got to have that occur. Okay. When we talk about likelihood of something happening, okay, 0.5 as a probability, it's 50-50 chance, right? So the closer we get to 1, the more likely something is to happen. The further we get away from 1 down towards 0, the less likely something is to happen. Okay, so anything, I would say, judging by this chart here, that unlikely is written close to where 0.25 will be, so 0.5% probability or 0.25 probability. Fairly unlikely that that's the case, but I'm a baseball guy, so Hall of Famers hit what to get a Hall of Fame? Great hitters. Chipper Jones just ended up in lifetime 300 hitter. That's 30% of the time. Not a really good probability, but for baseball, under relative circumstances, it's awesome. And this baseball, at that level, 300 is, 0.3 is really good. High school, 600 is probably what you would consider phenomenal in high school baseball, but professional baseball is 300. Complement of an event, complement with an E. So this is like complement from same word as you use in geometry. So complement of an angle in geometry was what do I add to it to make 90 degrees? Here it's denoted with a straight bar above the A of the event, whatever event it is. The complement of that is when it does not occur. Most of the time, if you're going to find the complement of an event, the best way to do that is how this example does, okay? It's easier to find the probability of that event occurring and then just subtract from 1 instead of thinking about, well, how many of these are not? You just find, okay, probability of it being a smoker from some data that we're given is 202 out of 1010, and then subtract that away from 1, and you get the complement probability of not being a smoker. So complement is the likelihood of that, or the probability of that event not occurring. So easiest thing to do is 1 minus the probability of the event occurring. A lot of times that's the easiest way to find that, and a better way a lot of times, especially as we get later in the chapter and the counting of the events gets a little tougher. Today, it's probably you can do it either way and be okay. But as we get closer to the end of this chapter, the counting of the events gets much more complex, and probability of smokers is obviously smaller here, and it's easier to count up. So when we get to more complex things, you need to remember that about complements. The 1 minus trick. That's going to save you a lot of headache. Trying to figure it out. All right, rounding off. So rounding rules for probability. I don't like these rules, but they're there and we need to follow them. Significant digits. It's not as it's clear as mud sometimes when we talk about significant digits. Mr. Wood and I had a conversation about that the other day because I knew this was coming up, and I was asking him what they did in chemistry for that. And he said, "Yeah, significant digits is how it's supposed to be done there." Okay, but exact fraction or decimal around to a final decimal results to 3 significant digits. 3 significant digits. Okay? So 3 significant digits. And we're dealing with probability. If it's an exact fraction, you can leave it that way, but like 2/3, 5/9, that's something. But if we're going to express it as a decimal, we go to significant digits. All digits are significant except for the zeros that are included in the proper placement of a decimal point. So if it's like 0.043, the zero that's after the decimal doesn't count as a significant digit. So we're not going just 3 decimal places. We're going until we have 3 numbers listed and then round. Okay, so it's 3 digits. The zeros in front don't count. The zeros in the middle or toward the back do count. Zeros in front don't count. That's kind of the best description I can give you. If you struggle with significant digits in chemistry or something like that, got to figure it out here. So make sure the zeros in front don't count. The zeros in the middle or the back do. We've talked about 0.685. Yes, the zero counts as a third one.
May I turn off the air?
Yes.
Sure.
All right. An event is unlikely if its probability is very small. For example, 0.05. That's a 5% chance of something happening. That's pretty small. Okay, it's a very unlikely event. Low number of outcomes or unusually high number of outcomes. Those are kind of like outliers of what we look for when we're talking about probability. So those are some red flags to you. If something is an unusually low number or an unusually high number of things happening, that event happening. Unlikely is 5% or less. Sorry. That's the claim. No, or quiz will be, yeah, Thursday. Is it Thursday? Okay, I didn't have it on my calendar. So it'll be Friday. Well, if you're gonna be back a little 31. Oh, 11:30 on
The name, so it's 0.25.
Not as unlikely, 0.2 is getting towards unlikely. An event is very unlikely if it's less than 5%.
But it would still be considered unlikely. It's not like
Yeah, still, I mean, it's the probability that it's happening, but if they say is this unlikely to happen, one out of 20 is pretty unlikely. That's what 0.05 is. So, thanks for reminding me of that. I'll put that on the calendar. We'll try to do this Friday. All right, odds. Odds are related to probability. Actual odds against an event occurring. So we're taking the probability of the complement over the probability of the event occurring. So flipping a coin, it's odds against that are 1 to 1. Heads or tails, either way. We're talking about drawing a heart. We would have odds against drawing a heart. That's 52 minus 13 over 13. Odds do not include the entire sample space. The unreduced form of the fraction for odds should add up to be the total number of events. So complement over actual event probabilities, that's how we find actual odds of an event. Odds in favor of are the reciprocal of that. Okay. So we take the probability of an event occurring divided by the probability that an event does not occur. So complement. And that is odds in favor of something. Payoff odds. This is an odd thing. It's for betting purposes. So increase your probability of doing well outside of school. Start betting on things and all that extra money you got when you go to college. So you payoff odds against an event occurring, the net profit. It's the ratio of the net profit if you win to the amount bet. Okay, so payoff odds against an event are net profit over amount bet. Okay. So that's based on, and we're going to see an example of this to start making it make sense. let me see this. So payoff odds, a little bit different. It's the net profit over the amount you bet. So this is when you watch Kentucky Derby and stuff, they payoff odds are like 35 to 1 or something like that. So that means for every $1 you bet, your profit would be $35. So if you bet $100 on that, you win $3,500 if that horse won. So the payoff odds are based on that. You bet on the wrong horse, you lose it all. So, like here's an example. You bet $5 on the number 13 in roulette. Roulette is the spinning wheel, spinning around. I don't know, but it's spinning around. It's got numbers. It's got black and red numbers. And you take a marble and just throw it in there, and it spins around, and the wheel's spinning one way, and the marble's going the other. And eventually, it lands in a spot, and that spot's what you bet on. You can bet on red. You can bet on black. You can bet on a specific number. Out of that. So if you bet $5 on the number 13, your probability of winning is 1 out of 38. That's probability of winning. And 13. So there's a 113 out of 38 numbers there. The payoff odds are given by the casino. They say 35 to 1. And you bet $5. Okay. The odds against the outcome of 13. What are the odds against the 13? If the probability is 1 to 38, 37 to how much?
37 to 1.
37 to 1 are the odds against that. Okay, so how much would the net profit be if you win by betting on 13? We bet $5. We won. All right, so this is how we do that. So not 13, 37 out of 38. Probability, the odds against that would be 37 to 1. That's what Aaron gave us. Okay, so there's our odds against. That's not the hard part. $35 profit for each $1 bet. That's what payoff odds tells us. Okay, so we bet $5. There's $175 net profit. How'd that get there? $5 times 35. That's how we made a net profit of $175. That's just for that one row. We ain't counting any of the other ones that we lost money on. We probably lost. So we'll make it. Okay. You get 13? No. Why would you play the lottery? You're betting when you play the lottery and that you will win. And odds of winning the lottery are very, very small. Roulette is less risk.
No, the lottery, you pay like $8 and then it's over. This is like, you keep playing,
well, it's easier to walk away from the lottery because you got to go to the store and buy a ticket. Here,
you just keep playing around and around.
You like blackjack, and you lose a ton of money doing that.
I'm good at that.
So, all right. No skill in roulette, though. It's all chance. All right. Let's get the next section.
I gotta go to a casino on this Thursday.
Yeah, we did a field trip to Gotta be careful with that. My thing, I don't go to those because I'm afraid I couldn't walk away if I won. I'm just
Yeah, the same thing. You can never walk away.
I don't think I can walk away. I used to date a girl, her grandmother like going and like for Christmas we get her a jar of quarters so she can go play slots. That's what she did. Man, it's the best thing for her. She loved it. She just like to go play slots. That's all she wanted to do. She wanted to sit there and play slots and go to a concert or something like that. All right, so section 4.3, we're gonna get the addition rule today. Okay, addition rule, and then Friday, I guess we'll get multiplication rule out of that since you guys are going to the college fair on Thursday. Next Thursday. You're trying to trick me.
Yeah, I tricked myself too.
Okay, as long as we're all in the same boat. All right, so this week we'll stay on regular schedule. Next week. Now tomorrow, I know Miss Bowen is going to come in and talk to you for a little bit about some senior stuff. So we may have to adjust from there. I don't know how long she'll take. if she takes the whole time and is working with all y'all at the same time, we may have to adjust from there. But
It takes the whole time.
well, it's some things I think some things you guys gotta fill out and things for various different things. But if she can get since all y'all are seniors, she asked if she come in here and just work with you guys. And she said, you guys are in the upper echelon of her career, so it should be easy for her to do that with you. So, all right, so let's get the addition rule, section 4.3. Addition rule is the device for finding probabilities that can be expressed as OR problems. Addition rule is OR. ORs are the addition rule. Addition rules are ORs. OR is used when you're talking about addition. Addition is used when you're talking about ORs. Okay, that's the thing you got to tie together here, so you know which rule to use. Because when we throw the multiplication rule in the next lesson, there's a different rule. We got to know when to use the addition rule. Addition rule is OR problems. Okay. Either event occurred, A occurs or event B occurs, or that they both occur. It could be something like that as a single outcome of the procedure. Okay, the key word is OR. This is an inclusive OR, which means either one or the other or both. Okay, OR, addition, OR, addition. And horse is dead. All right, compound events. This is where, section 2 is about simple events. One thing is happening. Compound events are what we're dealing with here. Okay, combining two or more simple events. That's what a compound event is. Blows your mind. Okay, notation, probability of A or B. What that means is probability that in a single trial, event A or event B or both of those happen. Okay. General rule for a compound event. Okay. Total number of ways that A can occur, total number of ways that B can occur, and then find the total way that we've got to take out the ones where it's like an overlap, where it's both of them happening. Okay. That's what the red part. Find the total in such a way that no outcome is counted more than once. So this would be like probability of drawing a 7 or a heart. So we have to figure out probability of drawing a 7. What's probability of drawing a heart? And then we got to take away what's probability of drawing a 7 that is a heart. So we got to figure those things in there. Okay. So we've got to figure out probability of each event occurring by itself, and then what if they occurred together? That's what we got to. And this is the formula that the addition rule deals with. So probability of A or B is going to be probability of event A plus the probability of event B, just separate. Okay, like they were individual events. And then we're going to subtract away the overlap, where they're both happening at the same time. So that's like, here's probability of 7s, that's 4 out of 52. Here's probability of a heart, 13 out of 52. How many 7s of hearts are there? 4. There's only one 7 of hearts. Yeah. Okay, so you would have 4 out of 52 plus 13 out of 52 minus 1 out of 52, because that's where it's both a 7 and a heart. Okay, so that's how that probability or event is going to occur, where P and B denotes the probability of them both occurring at the same time. Okay. All right. Intuitive addition rule says to find the probability of that, find the sum of the number of ways that A can occur, the number of ways B can occur, adding in such a way that it's only counted once. A or B is equal to that sum divided by the total number of outcomes in the sample space. That's an intuitive addition rule. That's one of those where you don't have as many numbers to calculate with that you're thinking, okay, well, this is the only way this can happen, this is the only way that can happen. Let's put them together. And there's no, then, well, that could have happened together. We'll see here. All right, let's look at disjoint and mutually exclusive events. Disjoint or mutually exclusive mean the same thing. I'm gonna say disjoint because I can't get mutually exclusive out today. My tongue is tied. Okay, so disjoint events mean they can't happen together. Mutually exclusive, they can't not occur at the same time. So there's no and. This is the easy part here when there's no overlap for that. Okay. And here's some Venn diagrams. Maybe been a while since you've seen a Venn diagram. They're wonderful things. Probability of A, probability of B, this overlap, this football shape in the middle is the overlap. A disjoint event, there's no overlap. They don't cross each other. Okay, so disjoint or mutually exclusive events do not have any overlap. There's no and involved. Okay? So we don't have to worry about that so much. So deciding if an event is mutually exclusive or disjoint at the beginning can help you when you go to find your probabilities. So that's one of the things you're going to have to decide at the beginning of your problem. Okay. A and A complement, they have to be disjoint, don't they? So if one's the complement to the other, probability of A is that we have a 7. The complement of having 7 is mean it's not a 7. So they have to be disjoint. It's impossible for an event and its complement to have the same things occurring at the same time. It's not possible. So, complementary rules, probability of an event plus its complement should add up to be 1. Those probabilities should add to be 1. Or you could end up with, here's that rule, that 1 minus the probability gets you the complement. If you happen to have the complement's probability, 1 minus the complement's probability gives you the actual event's probability. So those little formulas can be helpful when we start getting to more complex things. And this section is a little more complex than the first section, but not overly incredible. Here's the complement of event A. So here we've got probability of A is the circle, and the complement is everything that's not in the circle. That's what it's trying to show you. That's what the diagram is. Believe it or not, that's it. Okay, so what we're looking at here is some practice in implementing these formulas, and the practice for these for section 4.2 is starts on page 144. 1 through 49, I believe, is right. Oh yeah, and then for 3, short section here. That's why I put them together. Page 153, numbers 1 through 43. Okay. So start working on those. Again, you need to utilize your time today because Miss Bowen